All right, I want to go over the TreeStore. The TreeStore is especially important with Mumps because Mumps has a hierarchical or tree structured database. And what do I mean by that? Let's see here. I'm using this mesh database here. The mesh database, let me go up one level here, comes from the National Library of Medicine. I'm using a very old copy of it. You should not use it for clinical judgments or anything like that. I'm supposed to say that it's required. But basically, we've mentioned this before, it's a category or a part of the body. And then there are a series of codes. These are hierarchical codes to tell you how to get to that part of the body. So we see something a little more, somewhat tree structure. Because the eye contains that code. Eyebrows are that code. Eyelids are that code. Eyelashes, you see it's longer, but the first part's the same in each of them. Okay, where do we go from there? Down to my diagrams. These will be in the code that I'll upload for this video. First of all, here's a simplification of it. So this is, again, using the mesh. Mesh is pretty good, and that it is hierarchical and it's not terribly complicated. So we go to cardiovascular system. Cardiovascular system has blood vessels. Blood vessels are arteries, endothelium, vascular, microcirculation, and so forth. I better stop before I can't pronounce one of these. Under arteries, we have aorta, one of those, auxiliary arteries, and so forth and so on. These are all subsections of arteries. It's a branch there. Under aorta, we have aorta abdominal, thoracic, and that one. I won't try to pronounce it. And further down here, carotid arteries, and they go down to this and go down to that, and so forth. Now, those are codes. So if we start here, we look at how it would be represented in Mumps. First of all, Mumps, much like early BASIC, you had a command word, set. Later versions of Mumps of BASIC did away with that, but Mumps kept it. Mumps uses command words. Anyway, the up arrow means it's a global array. The name of the array is mesh. That you pick whatever name you want, as long as it's not already in use. And then you have an index. So the index A07, we put the value cardiovascular system. That's the thing at the top here. All right. Underneath it, A07, 231, we put blood vessels because that's the first thing underneath it. There may be many other things, but that's as far as we've gone right now. Under blood vessels, we put arteries. That's code 114 in the mesh table. So from A07, we go to 231, go to 114, we get to arteries. Arteries break down into aorta. There's the aorta. Aorta has three subcategories before you finally get to the leaves on this tree. And they would be aorta, abdominal, thoracic, and so forth. So you see, that's a tree description. It's a path description through the tree. That's how that works. And I didn't carry it all the way out, but that's what we're playing with. We'll be using those code numbers in order to build internally the tree. And at the end of the tree, or at the end of each one of these paths, we will have, I should say, and at the middle too. I mean, the top level one has something stored there. The top level, at the second level, is something stored. So you can store things at all levels. So at the very top here, it's A07, but I have stored cardiovascular system. Didn't spell it all the way out there. But that's how it works. Those are assignment statements, and you're creating, and these arrays are on disk. Okay, so it's effectively unlimited. All right, let's see what we've got next. Okay, here is a diagram giving you an idea of what they were originally thinking about. Is they thought of the patient record as a tree, where you've got the patient, then the patient subdivides into different categories, and then you've got for all possible admissions dates. For each given admission date, you might have a set of problems. For each problem, you have a set of data you collect, laboratory records, diagnostic, and so forth. And on and on and on. So it's a hierarchy. That's how they viewed it, and that's why they structured the database the way they did. And it was very successful, and it's still out there. Many hospitals still use systems based on Mumps. You don't see the Mumps. You're seeing your physician sitting there typing into a keyboard, but in many cases, the underlying system is in Mumps, and still works. So anyway, that's gives you an idea of what they were thinking of. It's a tree structure. So obviously tree stores in GTK are kind of interesting. All right, whoops. Okay, let's go that one. What if I took similar data, it's not the same data, but it's the basic idea, and mapped it out as a relational database? Relational databases are tables, and you get something that looks like this. I did this some number of years ago with the MySQL Workbench. Very nice product, by the way. I don't know if they still supply it. I haven't used it in years, but it was a really nice product to build your tables, and from this it would actually generate schema and interconnect them. So here we've got like problems, laboratory records. This is the table of valid laboratory records, which contain, information about the normals for each table. I only put low and high, but there could be, of course, many others. There's a limit to how much you can put on one slide. Then you have the actual labs, instances of labs that, lab tests that were done on a patient. And that would involve the patient ID, the diagnostic code, why are you performing this lab test, the onset of the diagnostic code. Someone may have a recurring condition, and the condition might be some particular diagnostic code, but they might have multiple onsets. There's many illnesses that recur. The test date, the test time, the test code. Now, test code relates back up to here. The result and a transaction number, some kind of unique transaction numbers are often used in these things. The ICD codes are down here, the problem codes, and the problem codes are also related to the patient, and everything's kind of interconnected. Now, bean counters like this kind of a arrangement, because now they've got all the lab codes in one big giant table, and they can scan them to find out, who's using what labs and, how much they're costing or whatever they're looking at. But they tend to lump everything into certain tables. And from the aggregate point of view, from a corporate point of view, that's nice. From a patient care point of view, it's kind of obscure. A big giant table of all the labs for all the patients in the hospital or in the hospital system is not very helpful to actually treating an individual patient. It has to be connected to the patient's record. Someplace in here is the patient record. Most of this is just data. It's the interconnects that make it a patient record. And that's not so visible here. Not structurally as you look at it. It would take a while to sort through it, and you would need explanatory notes and so forth, which wouldn't fit on the page. I took that data and I took that table, which I built myself, and kind of cut it up and said, what if I made it look like a table? Well, now it starts to look a little bit more like a patient record, because here's a patient, and then we've got stuff for the patient, different information like office visit, vital signs, history, doctor's appointments, insurance data for a given problem. We have the labs for that problem, the prescriptions, the notes, orders, radiology tests, prescriptions administered, and so forth and so on. So it starts to look more like a patient record when it's structured this way. But anyhow, that's the idea in Mumps is they are tree structured. All right, so I'll go back up here. This will be on when I'll upload all of that. Okay, I simplified the basic Glade file that I was using a little while ago, and I just have an entry box. I have 4 buttons down here, 4 GTK buttons. I have a text view in it's a viewpoint, and scroll window contains a viewpoint which contains the text view. The text view is where the text is going to appear. But because these other containers will get, we could get scroll bars and so forth to pop up as needed. I don't put anything up there that needs a scroll bar, but if you did, it would pop up. Anyway, down here, likewise, it's in a scrolled window. It's a GTK tree view. It's got stuff in it. It's got a selection entity, GTK tree select, which doesn't actually appear here, but it is an entity when you select something or select a row that occurs. Then you got 3 columns. Each of the columns has a renderer, GTK renderer, which tells how to render the characters. Generally, they're just the defaults I'm using here. But the columns have to be numbered 0, 1, 2, and the renders have to be numbered, named call 0R, call 1R, and so forth. That's the only restriction on the names. Anyway, and for each of these, we have like, okay, up here we get the tree store. That's the actual data structure where the tree is going to go into. It's going to be handled by GTK, but there is a data structure, and that's the data structure. The data structure is associated to the tree. You see down here under TreeStore, the model is TreeStore. Suppose that make that a little bit bigger and it won't jump back and forth. Yeah, this sometimes gets a little awkward to get everything positioned on the screen. But yeah, the tree one, which is a GTK tree view, has a model called TreeStore, and you can create them. I've already got one. I'm not going to mess it up. And that's where the data actually is going to be managed for you. Now the tree actually has no signals attached to it. Yeah, so it's just the tree. The signals are actually come out of the select entity, and there's a signal there on select one changed. Its name is select one, and so giving it the default name for the signal handler, it would be on select one changed. And we saw how to make that occur. It goes to the default. It uses on and then the name of the ID name of the entity or the widget, and then changed will be automatically inserted. Don't forget to hit carriage return. Anyway, so that's the signal that will be created if you actually select a row in here. Let's see. There's the button. So that's what that's what I've reduced it down to. Anyway, where are we in this? Well, let's run it first of all. Oh, what am I? The GTK mesh, which is, I'll click it over here because it comes up quicker without me actually typing the full name. That's the mesh database. Remember, don't use it for clinical problems, diagnosis, and everything. So there's the word, semicolon, and then there's the codes. The codes are separated by decimal points or periods, whatever you want to call them. Okay, and they're kind of related, but you can see they're longer and shorter and shorter. It's quite a large number, and I suppose the current list is even much larger, but I don't need to know the current list. There is a program here, which is, if you remember over here under GTK Mumps, the first thing it does down here is it says do up arrow buildtree.mumps. The do means to invoke that file, and the up arrow means it's a file. Up arrow generally means we're talking a disk, something on a disk. So the name of the program is buildmeshtree.mumps. Without the up arrow, it would assume I was referring to a label inside the program. It will run that program and control return here to this point. All right, that's the program which actually creates the database. The database, because I'm using the simplest database, is stored in key.dat and data.dat, which you may delete as if something goes wrong, delete that and then try something. Sometimes the database gets screwed up if you get seg fault or something like that. So they're just the simplest possible single user database. Now the program, again, I'm into mumps here, but anyway, I have to tell you how it works here. That destroys any previous instance of the database. I'm calling the database mesh. Okay, up arrow mesh is the name of the database. That opens the file, mtrees2003.txt. Old means it already exists. New would mean we're creating it. I'm not going to get into the details here. Test tells me whether or not the open succeeded. If it didn't succeed, we're done. I assumed it opened because it's there. For with two blanks after do means do forever. We use dots to indent, so this is one level of indentation. We switch to unit number one. Number one is the input. It is an input unit. It could be output. In this case, it's input. Because we said old, it means we're reading it. It exists. If we wanted to create it, we'd say new. Anyway, we switch to that unit. We read into a variable called A. If it fails, we stop. We extract from that line the part that's in front of the semicolon. One means the first part, delimited by a semicolon. And into code, we put the second part that's after the semicolon. That's the part, that's the thing, and the semicolon is the delimiter. So I get key and I got code. If either one of them are blank, bye, we're done. You notice here there's parentheses around the second one. Mumps has no precedence. Wow, you thought it was primitive. So in other words, if you didn't have the parenthesis, it would do this, is key equal to empty string, or code, it would OR the answer to that, 0, 1 with code. And then it would compare it with equals. So you have to put the parens in. It has no precedence. All right. For I goes from one, starts with one, from 1 by 1, no upper limit. There'd be another colon and an upper limit if there was. So in other words, incrementing I by 1 forever. And again, now you see we're into 2 levels of indentation. We put into a regular array. This is, remember, the arrays look like Fortran. And x sub 1, and I didn't kill it or create, because there's a new symbol table when we came down here. So there is no previous instance of x. There will be later, but anyway. I'm going to go up to a certain number of depth on these things. And they'll be erased, don't worry about it. Anyway, so I set in the piece of the code delimited by the decimal point, and I is the piece. So remember that we're in codes, we've got pieces that have decimal points in between them, and we're going to get, I is going to be the count. We're going to get the first piece, second piece, third piece. Now, Mumps tends to start with 1, not 0. Unlike other languages, it was back in those days you started with 1, not 0. Anyway, if you get an empty piece, you're done. You decrement I because you're out, by the way, of the loop at this point. So anyway, because you're back at the single level of indentation, you decrement I because that was an extra one. You switch to unit number 5. That's the standard console. This 5 is traditionally the console. It's very Fortran in that sense, which was also in use in those times. And I set a variable called z equal to quote up arrow mesh paren. What I'm going to do is I'm going to build a text image of a line of code, then I'm going to execute the line of code. So I started off with up arrow mesh, z contains up arrow mesh parenthesis. All right. Now I am going to go through the x. Okay, there's a loop. It's j. J goes starting at 1, incrementing by 1, up to I minus 1. Well, I is the total number of indices in this reference. I minus 1 is 1 less than them. I'm going to do it up to I minus 1 because what I'm doing is I'm going to say set z equal to what z was, concatenate. That's how you do a single quote. Within a quoted field, a single quote is a double quote. Again, that's very Fortran. Came from that error. It's not a backslash quote. It's a single quote. So that's a single quote. So a quote underscore the value in x sub j. Okay, one of those subcodes that I've pulled out of the code section of the current line that I'm reading in, concatenated with another blank here, with another quote. You have to quote all these things. They may look, they're not, yeah, they look like numbers, but get leading zeros on them we want to preserve. They are actually numbers, but it would lose the leading zeros in most cases. So I want to keep the zeros because that's part of the scheme. So it'd be quote and a comma. So it's going to have a comma in the string. Okay, so I take these things and I keep sticking them on to the end of this array that I'm building up, and I add a comma after each one of them. Well, the last one gets a parenthesis, not a comma. That's why I only went up through I minus 1. So after I've done that, I set z equal to set. I add, oh, by the way, I'm putting this word set in front. I didn't have the word set up here. I just had mesh. Now I'm adding the word set with a blank after it and concatenating z. And then here's another quote. This is the last one here. This is the ith one. This is the final one. And there's the quote. There is the close paren, an equal sign, a quote, single quote. Excuse me, that's the single quote right there. It's not easy to read at times. And concatenate with that the key, the actual first part of this line, the body part, and throw a quote in at the end. So now I've got a line that looks like an assignment statement. And it will look like something like this. What's in Z will look something like that. Okay. Then we execute it. We run it as though it were code, because it is code. It's an interpreter. I actually commented this. Pound sign's not a standard comment indicator for Mumps, but since I use this something like a bash script, I used pound signs legal in mine. Let's remove that. And let's see. We are in Unit 5. Just make sure before I run this that whether the output unit is correct. Yeah, it's Unit 5. We execute it. When this loop is finished, we will. This is the end of the loop here, and then I go back up here and I switch to Unit 1 again. And when I get down here, someplace in here, I switched over to Unit 5, probably because I was using this. So it'll print out the lines. I close Unit 1, switch to Unit 5, write out done, and end the program. Let's try it. Those are the lines of code it built and executed. So it built a line of code saying Z0, and these are place names down at the end. Place names are important in medicine, for where things originate and stuff like that. And the code is 600, and that's Indian Ocean Islands. And under Indian Ocean Islands are Comoros, Madagascar, Mauritius, and so forth. Okay, so those are the. I have that commented out because you don't want to see it every time. But those are the. That's how it builds the database. It's building the database. Let me go in there and get rid of that because I run this every time I go down there. I obviously don't need to run it every time, but I have a tendency to keep rerunning this. And all right, now if I run the thing, you won't see anything, and it basically just duplicating the same stuff in the. There's the word done at the end in the database. Okay, so there is that's how I built the tree. With that program, what is it? Build mesh tree.mumps. All right. Now, when I run this thing, what happens? We compile gtk.mumps. Okay, this gets compiled using my mumps compiler, but there's where the build goes. And there's where I did this the other day. I set up a string which I initialized the text buffer with. It's the text buffer you're initializing. It appears, therefore, in the text view. This is where you execute. All these plus signs mean this is a line of C++ code. It's C++. So you see plus sign include gtk1.h. It's including a file. It actually becomes a C++ include. And when it gets compiled, it actually includes GTK1, GTK2, and so forth. And then it does GTK4. Again, there's that running. It's running the file. I didn't put .mumps there. I just put .h after it, but it's executable. Then it does this, and then we go to GTK Main. Now we got the GTK Main sitting there waiting for signals. When it gets a signal, it calls a handler. Where are the handlers? The stubs of the handlers are down here. They're after the program. The Z exit ends the main program. The GTK3 are subroutines or functions that are inserted, which are the stubs of the on units to handle the signals. Again, I keep using the pale one term on unit. So let's see what these are. GTK1. GTK1, that's the declaration of all the variables I'm going to be using. And they're at the top of the program outside the main function, so they're global. Notice I've got GTK-X and GTK .h included. You have to have the GTK development code in there. If you've tried to do this and it's not working, you need to get the GTK development. I'm going to post an update to Mumps that actually, as part of the install, it brings in the GTK development options, the libraries. Okay, so that's actually a declaration of the variables, and you can see that occurs right here before main, so they're global. They're global. Okay, the next one is GTK2. GTK2, these are where it pulls out this function, Gtk Builder Get Object. Okay, Builder is the first object right up here. It's part of the automatic declarations there. What it does is it reads the Mumps GTK, the Mumps Glade file. This is part of C++. They're actually C functions. And it gives you back a pointer. This is the data structure that represents your Glade layout. Once you get Builder, fetch out the pointers to the individual parts. So let me get something a little more. For example, window. I call the function GTK Builder Get Object. I pass it builder, which is the pointer to the data structure for everything. And I say I want the window part of it. That name in quotes is the name of the ID from the Glade file. Okay, that ID you gave it in Glade, that's where you put it down. And it passes me back window, which is a pointer, which was declared in GTK1. All right. Then this business down here is I'm actually taking the value in the pointer window and I'm writing it into a temporary string, and then I am sticking that into the Mumps symbol table, and then I'm writing it out to a file, and the file, oddly enough, is up here. Here's the file open, gtk4.h, and it's open for write. So I'm writing these lines into gtk.4.h, which are basically saying what the reference or pointer is for each of these variables. I use them in the Mumps code. But anyway, that's what's going on. It does these all. It goes up, and I don't think there's anything else. Then at the very end down here, it does a signal connect, which you have to do. Connects all the signals for all those objects to their functions. The functions are there, by the way. They're loaded in at the end, as you noticed. And I connect the signal, connect the window. That's the destroy signal. Then the actual signals for the individual widgets, and then I show the window and I close that file that I was writing. Okay, nice and messy. Back to GTK. That's GTK2. Builds all that stuff. Do GTK4. What's GTK4? GTK4 is basically assignments. It's Mumps code. It assigns all these pointers, this is the file that was written by the previous program. It's read back in and assigns all of these pointers. These are the references that Mumps will use. When Mumps uses it, it needs a pointer. Mumps does not have anything but string data. So your pointers are reduced to string. Those are strings. They will change each time, of course, because your program's probably going to be in some other location. But anyway, then I do the build tree.mumps, and then the GTK main. Then GTK3 down here this was also created in one of those things. I think it was an extract widgets actually created it here. These are the stubs for all of the on units. You see extern C void on clear store clicked. Next one down here. On entry one changed. Next one down here. On select one changed. You see the names here. On find button clicked. All right. This is these functions have a calling procedure which is based on C, but they're in a C++ program. So that extern C void, all of these happen to return void. Some functions won't return void, but these all return void. But it's telling the compiler that these are C linkage, not C++ linkage. But anyway, for any one of these, let's see, on find button clicked, first of all, of course, it gets the widget W. It allocates, a lock SV is a function in Mumps. It allocates a state vector for the Mumps system. Let's see, it allocates a temporary string of 512 bytes long. It creates a line of code which is going to be set widget equals, and now we're into backslash because this is actually C code. That's %p, which means pointer conversion, and the rest of the line W here is the actual widget. Okay, it's a pointer. That's going to be put where the %p is. Okay, in there. So it's going to say set widget equal quote some pointer space go up arrow on find button one dot click dot mumps. So in other words, when you click find button clicked, when find button is clicked, this signal will be created. This signal will activate. It'll call this function. This function will assign to a string called widget the pointer value of the widget that came through as a result of the signal handler, and it will branch or call a program called on find button one on period find button period clicked period mumps. All right. When that program runs, it'll have available to it the variable widget which has the pointer in it, and it will run. It's a go to, not a do, which means return will not be made. The interpreter will, at the end of this, will quit. There's no reason to return. I'm not going to do anything. So go is different than do. And you can abbreviate everything as a single letter. In almost all cases, G means go to. Didn't mention that. I've probably done that a couple of other places too, and I didn't notice it. But G means the same. It's just shorter. And up arrow, of course, indicates that it's a file, a program on disk to be executed. So that's how they work. And I think we've gone through all of them, right? Except when we get down to the actual on units. Now, the actual on units that we go to here, let's try to bring it up and make it run. Well, I'm trying to do two things at one time there. Okay, that actually builds and compiles anything, but the interpretive stuff, the code that's interpreted doesn't have to be compiled. But yeah, it compiled it again, and so the GTK is the actual executable, and now it's running that build mesh. It takes a moment to run. That's why there's a pause there. Okay, so that's what you see. There's the test message, and everything looks neat. So the next one is load it. This loads the TreeStore as a tree. This loads it as a table. This is going to load the whole thing. This is only going to load about 100 lines of it, because loading it as a table turns out to be very time consuming because there's more to it. It's not nested. All right, so and you can see there's diagnostics popping in the background there. There it is. And if I go into any one of these here, you could see it's opening them up. And this is really neat from, because that's the Mumps database visually displayed. All right. That's the Mumps database visually displayed. And when I click on things here, that's actually GTK doing the clicking. I don't write the code. GTK sees me doing that and knows what it's supposed to do when I click one of these little arrows. All right. Now the question becomes, how is it doing that? So what's going on when you hit load TreeStore? Let's see if we can figure that one out. Okay, when you beyond load tree, this TA or TR, I'm hitting tabs in links. Okay, so this is the signal handler on load tree clicked Mumps. So when you click that button load tree, this is the Mumps program that gets invoked. And first thing it comes in and says do GTK4. Have you remembered GTK4? It says it's been modified, and I don't intend to play with it. It's GTK4, please. Hit the wrong one. It just sets up the it sets up the variable names with the values of the pointers. Because you say, well, didn't we do that already? Yes, we did, but each one of these signal handlers creates a separate stack entry, so it doesn't see the symbol table from the other ones, unless it came directly down after the stack was created. So yeah, so if you need it, that's where you're going to do it. And I do need it because it by default writes out a message saying, hey, we got clicked, and it prints out the value of widget, which is the pointer. All right, and then I say it returns a value. I'm not going to use the value. I think they got error messages in them. They've got numbers if there's an error message. But clearing the TreeStore. Well, TreeStore, where'd that come from? It came from GTK4. GTK4 instantiated the name TreeStore and gave a pointer value to it. Oh, yeah, as a string. But these things know about strings. So I'm saying clear out the TreeStore. Zap it. Okay, then I'm going to do the load tree view. I have to tell it where to begin. So when I do load tree view, this could be a go-to too, since I'm not really returning. The interpreter can terminate as soon as this is finished. Doesn't matter because there's nothing to return to. That tree is going to be the starting point. That tells it the starting point of where I want it to begin printing the tree. And up arrow mesh kind of means start at the top. That's far up as you can get. Then I run the program load treeview.mumps. We're getting there. All right. Load treeview.mumps. There's all this stuff at the front to make sure it's understood that it's open source GPL. In case somebody decides to say, well, I wrote it. No, you didn't. I wrote it. All right. Comes down here and asks the mysterious question, does TreeView exist? Is there value in tree? Is there anything in it? If it's 0, it means nobody passed anything down, so we're going to just start with the same as above. All right, so it just checks to see if there's anything in there. There's nothing in there, it sets it to, oh, it's always something in there, and I just realized there should be a set there. Since I never actually executed that command, it never told me there was an error. It's an interpreter. If you don't execute something, you don't find out there's an error there. But anyway, there you go, live debugging. All right, how many indices are there in the tree? If you've passed this entity down called tree. Tree could be a reference. It could be up arrow mesh, parenthesis, x, comma, y, comma, z, stuff in there. That would be the depth, the number of indices. So there is a function, a mumps function, $QLength, and you pass it down a variable, and it tells you how many indices there are. So that would be the depth of the tree, because initially it's 0. There aren't any. But it could be, if you could tell it to load at another starting point, and you could have a different depth. And there is, the search function tells it to start at a different depth. And so that's important. I set temp equal to nothing. Now this is the business if depth is greater than 0. And what it means is that you didn't give it up arrow ABC, you gave it up arrow ABC 1, 2, 3, something like that, something with extra indices. The problem is, if I'm going to start at that point, I just can't start somewhere in the middle of the tree when I write it to GTK. GTK expects there to be parents going to the top. There has to be an origin, and so they'd have to be, so in this would imply I'm starting at 1, 2, 3, 4, and next one might be comma 5. Next one might be comma 5, so 6, something like that. What happened to 1, 2, 3? You got to write them in. You got to tell GTK about 1, 2, 3. That's what this is going on here. All right, and I don't want to play with that because it's another one of these tripping over double quotes. But that's what it's doing. It's going to create the ABC1, ABC1, comma 2. ABC1, comma 2, comma 3, and instantiate them. So, but anyway, it's that special case. If you come down with just plain old mesh or just a plain old global array variable, still works for others. I've not tried it with any others, but it should. Then you come down here. This would be irrelevant because the depth is 0. You wouldn't do that. I'm not going to worry about that right now. It's too far into the weeds. How the basic thing comes down? What do we do? Forever. Notice there's blanks. Blanks are important delimiters in mumps. If knowing exactly how many blanks to put someplace, it makes a big difference. The 2 blanks tells it there's no argument. There's no for I equals 1 by 1 to something really. The blank stands for the missing argument. So there's 2 blanks in there. There wasn't an accident. Do also has a situation like that too. But anyway, that creates a do group. This is the block. It enters this block. You see there's one level of that. Okay, what query does is I pass down to it tree. Okay, I pass down at tree, which is how it knows to actually execute the tree itself. It's part of the weird syntax, but I'm passing down essentially up arrow mesh, or at up arrow mesh is what it's seeing. And as a result, query will find me the next ascendant element in the tree. So if you think of the tree like it was over here, at the very top here, well, it'd be just plain old mesh, but say it's A07. The next ascendant is alphabetically after it. It's A07, and it will be the first index underneath A07, the lowest value. So if there was A07, comma 131, you would see 131 presented. It gives you the next value in the table. These are presented, as far as it's concerned, alphabetically. It's going to be alphabetic by the first one, alphabetic by the second one, alphabetic by the third one, presumably the first are all the same, and so forth and so on. So so when you do a query, if I did a query on A07, I'd get this one. If I did a query on this one, I'd get this one. If I did a query on, and so forth. This is the order in which they'd come out. And there's nothing in between. There's 231 has only, the first descendant of 231 is 114. There is nothing earlier than 114. You can actually go backwards. There's a way to go backwards in these things, but we just stick to going forwards at the moment. So it'll give me the next descendant. So if up arrow mesh is my initial one, the first one I'll get is up arrow mesh parenthesis A01. It'll have quotes around it, but yeah, so it's the very first one in the tree. If it comes back empty, it means we didn't find anything. The queue length tells me how many elements. Well, how many elements is the depth of the tree? How deep the tree is, how deep the reference is. Okay, now this goes back to depth was calculated up above, and if the tree is empty, where am I here? This is a break. So in the other one there, where I came down with something deeper, and I wanted to only get things deeper than that, when I finally retreated back up to something which was of at least the original depth of the original query, I don't want to go on. I'm finished. We'll see that in an example, but that's for the other case, the search case. So don't worry about it. In the case of up arrow mesh only, the original depth is 0. So the only time we're going to get back to 0 is when we run out of stuff, and we're already out of here because we ran out of stuff. All right, percent. Percent's a variable name. You can use percent in variable names in Mumps. It's a throwaway. I'm not using the value, so sometimes I just use percent when I tell them to remind me that I'm not using it anywhere else. $Z, you're going to have that, and a whole bunch of squiggles separating. That's actually the name of the function in GTK, but it's actually implemented in my code. You pat TreeStore, that's what we're storing it in. The depth of this thing, it needs to know that, because internally when it's building the tree in the first column is the tree. The other columns are just flat. The first column is the tree. So the entity I'm putting in is at this level of depth. That's the entity I'm putting in. That's the contents of the entity. So this might be up arrow mesh A01. This would be whatever that was. I forgot. Body regions. Where is it here? Oh, see if I've lost it. Of course, I've gone down too far. I've gone up too far. There it is. Body regions. A01 is body regions. Okay, so if the thing here is up arrow mesh the parenthesis quote A01 close quote close paren, then the value of at tree will be body regions. It'll be a string which is the contents of it. All right. The at sign says we don't want the reference. We want what the reference contains in this case. All right. So that would be so. In other words, this is the thing that's getting put into the. This is these first three things are actually the tree. This is the actual TreeStore. This is the depth. This is the entity at depth, and then the rest of this is the row. There's three elements, 3 columns in the row. So for once we've gotten down to a level, once we've inserted something like abdominal cavity. Abdominal cavity has the remainder of its row will contain, well, abdominal cavity, and it will contain the last element, last index in the reference. So if the reference is A01, 220, I made that up, this would be 220. And what it is, Q subscript is a program, or is a function, which when given an array reference, gives you the ith index of it. So the ith index, this is the depth of it. That's the last index. So this guy here is the third column. This guy here is the second column. This combination here is the first column. The first column is a tree, is organized as a tree. And that's what's going on. And again, go back to refresh your memory as we run it here. And it does that rebuild every time. So I load the TreeStore. Okay, so let's say A01, there's abdomen. If I click A01047, this is the tree part. This is for this particular entity, this row, the value of that is abdomen, and 047 is the last element to it. So actually the tree is the first column, and these are adjustable, by the way, in Glade as to where how big everything is. There's settings in there. So if I click down one more, again, here's the row. And again, this is organized as a tree. These are just flat rows attached to an entity in the tree. So this is an entity in the tree, and clicking it there caused it to pop up here because I executed the select by doing that, and select read what was in there and wrote it up here to the text view. All right, so there it's got three entities. The value of it is abdominal cavity, and the last one, I just put that in there. It has no overwhelming significance other than the fact I could prove I could do it. If you wanted additional columns, you could, as a result of clicking on something, you could calculate something and put it into one of these columns, and so on. So yeah, so this is the treeness is over here. Some of them get kind of deep. I think if you get too far in some of them, they actually run out of space here. But this seems to be the deepest I've found. It's got 1, 2, 3, 4, 5, 6 levels of depth into the tree. And that is the metatarsus. And the last code on it is 480. So that's how that works. There's another one here, which is load table, clear store, and then load table. This is purely flat. It's every one of these things just flat. All right, they're the same values, and a given row, there would be a row in the tree version which would say this and would say that. I just put null. That's not them putting null. That's actually I used the word null in the code. I didn't bother to pull it out. I certainly could have. I just didn't. But anyway, it's a flat presentation of it. It's a table. I only did the first 100 because it's really messy. Let's look at that. It takes too long. Load table, not Mumps. It's much simpler. I see there's for the first 100, 1 by 1 to 100 do, and then we're into a block. We just simply query it, same as before. We get a row, we get an element in the tree. If it's empty, we break, and we simply store it there. They're all at level 1. They're all at tree level 1. So there's the actual tree reference, there's the contents of the tree reference, there's the word null right in there. So yeah, the table version is much simpler. That just treats it as a table. There is no tree. You didn't store it as a tree because it's all stored as a tree at level 1. All right, this has probably been way too long, but hopefully that will show the correspondence, because in Mumps, of course, because it is a hierarchical database, it's really nice to have a way of printing that out or showing it, displaying it in a window, in an app window. And there shows how it can be done. Now you can mix and match and restructure this any way you want, but that's basically the way to do it, to put it into a TreeStore. There's other ways of accessing it, no doubt, but that's actually how to display it. Now, this is still ongoing work. It's kind of experimental at this point. I'm adding to it. If something blows up, feel free to send me some of the debris, and I'll see if I can fix whatever's gone wrong. I'm going to try to implement as many functions from GTK as possible, but I think the ones that are in there, which are in user notes, which I mentioned last time, was a pretty good selection for a lot of basic things. Now, of course, there's a million more, but trying to just get the basic ones that people would use to actually write real-world examples quick and dirty. And that's one of the nice things about Mumps is you can write code fairly quick and dirty. All right, I'll quit at this point.